Now we can talk a little bit about electromagnetic force, which is going to entertain us for at least the first part of this term, and really for most of the term. So we mentioned with the triboelectric effect that a balloon gets stuck to your sweater, and we always, when you ask why that happened when you were a kid, you said, well, it's static electricity. But we want to think a little bit about what that means. What is static electricity, and how is that holding your balloon to your lovely blue and white striped shirt? So let's look at a free body diagram. I know you're groaning. Yeah, we still have to talk about forces. Forces aren't going away in 152. They're still going to be with us. So we'll draw a free body diagram of our balloon. It's got a weight force, right? It's pulling it down. It's got a buoyancy force because it's displacing the fluid in the air. That's not a very large force. It's got a normal force because it's pressing against that shirt. There's nothing over here to hold it to the shirt, right? This is the sweater over here. Um, and so we want to figure out what that is. That's our electromagnetic force. So let's balance this problem. So to think about what that electromagnetic force is, we're going to take a giant step back and think about the kinds of forces there are in the universe. Um, there are two of them that we're going to talk about very little in this class, which are called the weak and strong nuclear force. They act on very, very tiny scales, um, and mostly within molecules. And so we can ignore them for the most part. Gravity only acts with hugely massive objects on any kind of human scale. So that clearly does not explain the attraction between the sweater and your massive um, midriff. So what is the one remaining force? That's our electromagnetic force. If you think about this, these are all pretty limited in the way that they're acting on our everyday lives. I mean, they're all fundamental to the world we live in. Um, this explains an awful lot, right? So if you want to talk about the tension in a spring, that's really about uh, varieties of the electromagnetic force working between molecules, pulling and pushing in intermolecular forces. That's what's holding up your chair on the floor, that molecules in the wood floor don't want to be split apart from each other, and they're going to be compressed, and that presses them together, and electromagnetic forces push back up on your chair. All of this stuff has to do with electromagnetic forces. Still, doesn't quite answer our question. So electromagnetic forces exist between carriers of different charge. Now we sort of saw that when we talked about charge last time, right? If I put um, that charged rod next to those two metal balls, the positive charges in the rod attracted the negative charges in the balls. Those negative charges were moving, right? They were accelerating. So we know there has to be some kind of force there that is moving those charges. And that's the electromagnetic force. It pulls together unlike charges and pushes apart like charges. So down here, if we have two negative charges, they're going to tend to be repulsed from each other. If we have a positive and a negative charge, they're going to be pulled towards each other. And when they don't have any kind of velocity, we call this an electrostatic force. That is, they're like statics before. There's not much moving, and so we're just interested in the way that they're acting on each other without the effects of movement between them. And Coulomb's law is the equation that tells us what that electrostatic force is. K here is a constant. R is the distance between the two charges. Here's that R. And Q1 and Q2 are the amount of charge that Q1 and Q2 hold. So you can see as they get farther apart, the electrostatic force between the two particles is going to get smaller. As their charges get larger, they're going to be, the attraction or repulsion between them is going to get stronger. And it's just worth noticing as we think about the sort of fundamentalness of these forces, how similar this is to Newton's law of gravitation. It's a constant, G or K, times the quantity that the force acts on, mass down here or charge up here, divided by the square of the distance between them. So they're very similar in form, and that suggests in some ways that they have that fundamental connection as basic forces in the world. Now, we can also talk about the electromagnetic or electrostatic force acting on insulators as well as conductors. Um, they're not going to be as affected as a conductor might be. But as you can see over here, if this is our conductor or our insulator here, an insulator doesn't have those free electrons that can move around and move over here to this side, well, up here, I guess, with the positive, over here to this side of the container. But the individual molecules can be polarized. And this is particularly true for some naturally polarized molecules, like a water molecule. If you remember from chemistry, a water molecule's got the two hydrogens and an oxygen, and that unsymmetrical shape means that it has a strong polarization. And so here's a nice image of water being affected by a charged rod. So that charged rod can pull these electrons here, or the polarized side of these molecules is more attracted to the rod than the positive side is repulsed, because that positive side is just a little bit farther away from the rod. So there's that R square acting. And so in net, it's going to pull this material towards our charged rod. So we go back to our balloon question and we can kind of think about, okay, let's see what's happening in particular there. This is a chart of triboelectric characteristics in different materials. And you can see that wool is going to tend to be positive, and a rubber balloon is going to tend to be negative. And so that balloon is more attractive to negative charges. When I rub them together, those electrons are able to leave the wool and move on to the rubber balloon. And so then I have two charged objects. I have a negatively charged balloon and a positively charged sweater. And those two things are going to be attracted to each other. And the Coulomb force between the two of them, the electrostatic force between the two of them, is strong enough to pull that balloon towards your sweater. And so here we can write our Coulomb's law here, our Q of the balloon and our Q of the sweater, divided by the distance between them squared. And that's how the electrostatic force works in that particular situation. So that's what we mean when we say static electricity.